Hello, welcome to another CHEM271 tutorial. So this one we will be going over a practice midterm. This is practice midterm 3. However, this is sort of the material that you would see on the second midterm exam of CHEM271. So this one is going over enzyme kinetics, inhibition, chemotrypsin, ATCase, that kind of stuff. So if you want the acid-base midterm stuff, that is the previous two midterms. So this is going over the second third of CHEM271. So our first question is asking, at what substrate concentration does an enzyme function at 1/2 its maximum rate? So essentially what we're saying here is V0 is going to equal 1/2 V max. Okay, so here we can just use the hyperbolic equation for enzyme kinetics, and we can just substitute this in. So we get 1/2 V max equals V max times substrate divided by Km plus substrate concentration. V max cancels. So now we can multiply both sides by Km, and we can also multiply both sides by 2 as well. So if we do that, we get Km plus substrate concentration is equal to 2 times the substrate concentration. So we subtract the substrate concentration from both sides, and we get Km equals the substrate concentration. That makes sense because we know the definition of Km is the amount of substrate needed to reach 1/2 V max, or the sort of at the substrate concentration of Km, that is when half of all enzyme active sites are filled, and that's when we reach 1/2 V max. Okay, so define Kcat. So this we know is the turnover number. That's the formal definition, but it's also the rate at which substrate is converted into product by an enzyme. Okay? So it's the rate of the dissociation of the enzyme substrate complex into enzyme plus product. That's another way of thinking about it. And if we want to calculate it, we use the equation Kcat is equal to V max divided by the total enzyme concentration. If you want to see an example of this calculation, I show it off in the enzyme kinetics video. Okay? Question 2, does a non-competitive inhibitor increase or decrease an enzyme's apparent V max? So a non-competitive inhibitor will decrease V max. Why will it decrease V max? So a non-competitive inhibitor, remember it binds to, if this is an enzyme here, and this is the substrate, the inhibitor will bind to a secondary regulatory site on the enzyme, not at the active site. So essentially, the non-competitive inhibitor does not impact at all substrate binding. So no impact on substrate binding to the active site. So because there's no change in substrate binding to the active site, it takes the same amount of substrate to fill 1/2 of all enzyme active sites. So Km is constant. However, Vmax decreases because what's happening is when the inhibitor binds to the enzyme, that changes the conformation of the active site and makes the enzyme less able to convert substrate into product. So it decreases Vmax because it decreases Kcat, right? It decreases the rate at which substrate is converted into product. Okay? So does not impact substrate binding, but reduces the capacity of an enzyme to convert substrate to product, reduces Kcat. It also, Vmax also decreases because the rate of reaction when all active sites are full, so all the enzymes have substrate, is decreased due to the sort of inhibition of the ability of the active site to catalyze the reaction. All right, next question. So part A asks us to simply just draw a Lineweaver-Burke plot given this data. So remember Lineweaver-Burke plot, this is the double reciprocal plot. So we're graphing 1 divided by the substrate concentration versus 1 divided by the rate of reaction. So when we plot these, we should get a straight line, and I've already plotted the points here, so if I connect them now, we get this line, and then if I keep going, we can see we have a y-intercept and an x-intercept. So remember that the y-intercept here, this is going to be 1 divided by Vmax, and this x-intercept here is going to be -1 divided by Km. So that's why we use a Lin-Weaver-Burke plot, because from these intercepts we can then calculate Vmax and Km. We can actually quickly try to approximate these here, right? So we can see that 1 over Vmax is roughly equal to 3 over 4. So Vmax is probably roughly equal to 4 over 3. And we can see -1 over Km is roughly equal to -1.5, or 3 over 2, right? So Km is probably roughly equal to 2/3. But we can now try to figure these out by using some algebra. So we can find the slope of this line. So we know that the slope of a Lin-Weaver-Burke plot is going to be equal to Km over Vmax. Okay? So what we can do is find that's the slope m is equal to y2 minus y1 over x2 minus x1. We can pick any 2 points. I am going to pick 8.5, 5, and I am also going to pick 0.5, 1, so just the first and the last point, okay? So we get m is equal to 5 minus 1 divided by 8.5 minus 0.5, and we get that this is equal to 4 over 8, which is equal to 1/2. Okay, so the slope of 1 over 2. Next up, we can calculate Km and Vmax. So we know in the equation, we know that our y-intercept here, so B is going to be equal to 1 over Vmax. So thus we know Vmax is equal to 1 over B. And we know that our slope is equal to Km over Vmax. So thus we can say the slope times Vmax is equal to Km. Or we can say that by combining these two equations, we can say that the slope divided by the y-intercept is equal to Km. Okay? So now we have an equation to calculate Vmax, and we have an equation to calculate Km. So what we can do now is, we should have calculated B a while back, but to calculate B, we use y. Y equals mx plus b, so we know b is equal to y minus mx. We can sub in a point here for this, so let's use this point. So b is equal to 1 minus 1/2 times 1/2, which b is equal to 1 minus 1/4. Okay, so b is equal to 3 over 4. That's exactly what we predicted from our graph. So we know now Vmax is equal to 1 over B, which is equal to 1 over 3/4, which is equal to 4/3. And we know Km is equal to m over B, which is our slope that we found here, so 1/2. And we know B is equal to 3 over 4. So 1/2 divided by 3 over 4, which is equal to 1/2 times 4 over 3, of which we get that Km is equal to 2/3. So I know we were able to find the exact same answers from just the graph, And that's a perfectly valid way to do it in Excel. However, on an exam, you would want to calculate it this way. All right, 2 more questions this time. So the first one is asking us to define catalysis by approximation. So this involves an enzyme bringing 2 substrates together. So, and this occurs along a single binding surface of the enzyme. Surface of the enzyme. So what does that mean? So essentially we can look at an example here. So we're going to look at carbonic anhydrase. We'll talk about this a little bit more later, but the way this works is it has a zinc ion and then 3 histidine residues in this sort of geometry, and then this will be bound to an OH. So this OH here is from a water molecule. So this is from H2O, but it's lost a proton and has gained a negative charge. And then what happens is carbon dioxide here comes in, and now that this O minus, it's a good nucleophile, you can do a nucleophilic attack on the carbon, like that. So essentially, what we see here is that H2O is in close proximity to CO2. The other thing to note here is that this has to be in an orientation that facilitates catalysis. So essentially here, what's happening is, yeah, they're being brought close together and the oxygen is nucleophilic, so that can do an attack on the carbonyl in the CO2. And just as a note, the end goal of this reaction is plus H2O, so carbon dioxide plus water form bicarbonate, HCO3 minus. Okay, so we'll discuss carbonic anhydrase a little bit more later, but that's just kind of the base mechanism. It's an example. Generally in an exam, you want to give an example for this kind of question. Next question, draw the Cleland notation for the reaction given it has a random sequential mechanism. So this means that the order of the addition of substrates and the release of the products is arbitrary. So substrates can be added in any order, products can be released in any order. So this is what the Cleland notation looks like. So here we have an enzyme. Let's see if I run out of space for drawing this. So we have a hexagon here. Another hexagon here, and then we're left with just enzyme here. So essentially, we have A and B, those are the reactants. Those have to enter the active site, but they can enter in any order. So A plus B enter active site in any order. That's what a random sequential mechanism is. So here we have one possibility. Let's say A binds first and then B binds second. So what happens first is we get a brief transition state where enzyme is just bound to A, so EA. The other option is substrate B will bind first and then substrate A will bind second. So here we get a brief transition where only substrate B is bound to the enzyme. So enzyme bound to B, okay? So now what happens is the enzyme is bound to A and B at this point after it's bound both substrate in any order, and then it will react to form enzyme bound to the products, C and D. So C and D leave the active site in any order. So let's say C leaves first, right? C is leaving first. When C leaves first, we're left with the enzyme bound to just product D. So then D can leave second. And then that just leaves us with just the enzyme, nothing bound to it. Alternatively, D can leave first, and then C. So we're left with a brief transition of just product C being bound to the enzyme. So that is the full Cleveland notation given it has a random sequential mechanism. All right, the next problem, problem 6, asks us to draw the mechanism for the deacylation steps of peptide bond cleavage by chemotrypsin. So this is steps 5 through 8. I've actually made a separate video detailing the chemotrypsin mechanism, so we will skip this problem just in this practice exam. If you'd like to look over it, I made a separate video on it uploaded to this channel. So question 7, in carbonic anhydrase 2, there is a histidine residue adjacent the enzyme's active site. What is the role of this residue? So this is sort of subbing for histidine here, but if we want to draw it out, looks something like that. So essentially, what is happening here is this histidine residue acts as a proton shuttle. So histidine. And this is in carbonic anhydrase. We already saw it. It converts carbon dioxide and water into bicarbonate. Okay? So in this case, the histidine is going to be transferring the H from H2O to a buffer, which we can just call B. Okay? So the first thing it's going to do is it's going to be to deprotonate the water. So, and then the next part of the mechanism is that a buffer can come and pick up the hydrogen and give the electrons back to histidine. So essentially here, this is going to protonate base. If it's deprotonating, this is acting as a general base. And then if it's protonating, this is acting as a general acid. All right? So in this case, the buffer is what is deprotonating the histidine, not the water. So this ensures that the water is not reprotonated and that this is not reversible. So that's it for this problem. Okay. Question 8. This compound is about ATCase. So it's saying mercury compounds can bind to the zinc fingers in ATCase. So how does mercury binding impact ATCase activity? So let's first look at the structure of ATCase. So it has this C3 in the center. So C3, this is the catalytic domain. Okay. And what's not shown here is that there's actually another C3 below this one. So there's actually 2. So there's another one below it, so sort of into the screen, if you will. So this forms a C6 total. So there's 6 C subunits, 1, 2, 3, and then below another 1, 2, 3. These are the regulatory subunits. So R, and there's 3 R2, so 1, 2, 3, 4, 5, 6. So this is R6. Okay, so we have times 2 of the C3, which gets us to C6, and we have times 3 of the R2, which gets us R6. So the full ATCase is equal to C6 R6. So looking at this now, zinc is critical for the interactions between C and R subunits. So normally cysteine residues form the interactions here and they bind to the zinc residues. However, mercury compounds will bind to cysteine so that the cysteine can no longer bind to the zinc. So thus, there are no more interactions between the R and the C subunits. So the enzyme will dissociate into C3 and R2. So without any mercury, you get C6R6, and this has catalytic activity. It also has allosteric regulation. So one of the most important things about ATCase is that it can be regulated allosterically. With mercury, though, we split apart into C3 and R2 subunits. So C3 still has catalytic activity, but no allosteric regulation. Okay, no allosteric regulation, but it does still have catalytic activity. The R subunits by themselves have no catalytic activity. They don't normally catalyze the reaction. And they can't do much else, but they can still bind to CTP. So that's really all they can do. All they can do is just sort of bind to the regulator, but that doesn't do anything because it's not bound to a catalytic domain anymore. So now kind of looking at the ATCase over here in a little bit more detail. This is not part of the question. That would be enough to answer the question. But here, I just kind of want to show off the R state and the T state. So this is what it looks like from the side view. So you can see this is the C3 in the R state. So there are two C3 subunits, and they're connected by these R2 subunits. In the R state, where the enzyme is active, there's sort of an opening between the C3 subunits. But in the T state, the C3 subunits are closer together, and thus it's not able to catalyze the reaction. So R state, remember, is active, same as hemoglobin. T state is inactive. And when CTP binds, CTP keeps it in the T state. So T inactive, so CTP inactivates. What ATCase is doing, this is part of nucleotide biosynthesis. So the CTP is cytidine triphosphate. So this is sort of something at the end of a metabolic pathway, and this is an example of feedback inhibition, where the CTP made at the end of the pathway will come back, bind to an enzyme near the beginning of the pathway, and inhibit it. So if there's too much buildup at the end of a metabolic pathway, what happens? The pathway gets shut down through feedback inhibition by, in this case, keeping ATCase in the T state, keeping it inactive. All right, two more questions. Question 9. What reactions do kinases catalyze? What substrates are involved? So these catalyze phosphorylation reactions. So kinases catalyze phosphorylation reactions, which look something like this. Substrate plus a phosphate group forms a substrate bound to the phosphate group. Okay? Enzymes themselves can be a substrate of phosphorylation. Specifically, so enzymes can equal substrates. Not all the time. This can also happen to regular chemical substrates, right? So specifically, it is the serine, the threonine, and tyrosine subunits that can be phosphorylated because they have an OH. These all have OH, can be phosphorylated. And also, the last thing is PI can, so this is the phosphate group, can come from ATP. So in this case, if like an enzyme is being activated through phosphorylation, you could say enzyme forms enzyme phosphate, and the phosphate would come from ATP. Hydrolysis, ATP. So the phosphate comes off the ATP and forms an ADP. This requires a water too, right? So, all right, question 10. Draw D-glucose and L-glucose in both the Fisher and Hawthorne projections. So this is just something that you'll need to memorize to start out with. So what we essentially start out with is the typical pyranose structure for the Fisher projection. So 6 carbons as such, CHO at carbon 1, CH2OH at carbon 6. Okay, so for D-glucose, again, this is just something you have to memorize. So the first OH is going to be on the right, second OH on the left, third OH on the right, and the next OH, so the OH on carbon 5, is going to be on the right. So the C5OH, if it's on the right, that gives us the D configuration of glucose. Now for L-glucose, what we're going to see is the reverse of these. So OH on the left for this carbon, carbon 2, and then OH on the right, and then OH on the left. So for carbons 2, 3, and 4, this is completely backwards. It's also going to be backwards for carbon 5. And here, the C5OH on the left, that's what tells us that this is the L sugar. Okay? Now for the Hawthorne projection, so these are looking at the hexagonal ones. We're going to look at just the alpha ones here. Okay? So essentially, if the we can number the carbons as such, 1, 2, 3, 4, 5. Carbon 6 will be coming off of carbon 5 here. So what we are looking for is if the OH is on the right, this will be going down. If it's on the left, it will be going up. Okay? So for carbon 2, 3, and 4, we can draw it as such. OH, H, OH going up on carbon 3, OH going down on carbon 4, and on carbon 5, the CH2OH, that will be pointing up, because if it's up, this is a D sugar, okay? And then H pointing down. Then coming off of carbon 1, we are going to have the OH going down. Why? Because this is alpha, so if it's alpha, that means that the CH2OH and the OH are opposite, so OH opposite of the C1OH. Okay? So for L-glucose, we just kind of do the opposite at every carbon. So for carbon 2, again. For carbon 2, this one will be going up. Carbon 3 going down. Carbon 4 going up. Carbon 5 going down. Carbon 5 is going to have the CH2OH going down. Why? Because down gives us the L conformation, and then here we have the OH going up, such that it is opposite the CH2OH to give us the alpha configuration. So you do have to do some memorization here, but if you know how to convert between Fisher and Hawthorne projections, you don't have to memorize too much in order to figure a problem like this out. All right, these are the last two questions of the practice exam. So number 11, why is beta-D-glucopyranose the most stable monosaccharide? So let's first compare alpha-D-glucopyranose to beta-D-glucopyranose. So the alpha one, remember these are anomers, so they only differ in the stereochemistry at carbon 1. So this is carbon 1, okay? So here in the alpha one, the OH is opposite the CH2OH, so that gives us alpha. In the beta one, the OH on carbon 1 is on the same side as CH2OH, okay? So the reasons why beta-D-glucopyranose is stable, first off, it's a 6-member ring. So this is stable because it has a 109.5 degree bond angle. So this leads to low ring strain versus a 5-member ring, 4-membered ring, or even going up. This one has the lowest ring strain. It's very close to the, it's able to form like a chair conformation where all the bond angles are sort of the ideal bond angle for the sp3 carbons, okay? Second, in the beta form, in the chair conformation, all CH2OH and OH are in the equatorial position. So remember, axial position would be going straight down or straight up from a carbon, but equatorial positions are kind of going off to the side, so they're extending off of it, meaning when you have them all sort of in axial position, so like you have an R group and an R group, what happens is you get steric interactions. But when you have the R groups in equatorial, you don't have the same steric interaction because they're farther apart. So because of that, the equatorial positions are more stable in this case because it minimizes steric interactions. These groups are farther apart, they're not facing each other at all. They can't really interact in any real way. Thus, because the beta form gives all of these groups in the equatorial position, not the axial position, that makes it the most stable, okay? Last question, number 12. Part A is define anabolism. So these are reactions that build large complex molecules from simple, smaller molecules using energy. So this is biosynthetic reactions. Okay, so these are reactions that are building things up. An example of this would be glucose turning into glycogen. So this is taking a lot of small, simple compounds, putting them together, and these usually use energy, which can be in the form of ATP or NADPH. This is an electron carrier. It will transfer high energy electrons to compounds, allowing further biosynthesis. Okay? B, define substrate level phosphorylation. So these are reactions that produce ATP or GTP. So an example of this would be like 1,3 is phosphoglycerate, so this is from glycolysis. Plus ADP. So a phosphate will come off of the 1,3 bisphosphoglycerate. It will phosphorylate the ADP, and this will form 3 phosphoglycerate. So only 1 phosphate on this. So this one has 2 phosphates, this one has 1, and one of the phosphates comes off of this one, phosphorylates the ADP, and makes ATP. Okay? So it's a reaction that generates ATP. So that will be it for this practice exam. There will be one more practice exam after this, and then that should cover all of the material for your second midterm. Thank you for watching.